Hello everyone, my name is Neha Kardam and this is the first lecture on operational amplifiers. Operational amplifiers, they are also called op-amps, and in this particular lecture we will be seeing the basics of op-amps, and then we will talk about different applications, properties, and then later we will see the inverting op-amp. So let's get started. Introduction. So a PAMP is a short for operational amplifier, and operational amplifier is molded as a voltage controlled voltage source. An operational amplifier has a very high input impedance and a very high gain. So this the last point which you see is one of the important property of an operational amplifier. And these operational amplifier, they are basically specially designed amplifier in bipolar or CMOS with typical characteristics. For example, as it says, the last point, it has very high gain, and this gain will be in 10,000s to almost 1 lakh, and it has differential input, and as it says, it has very high input impedance. It has a single-ended output, and it has very low output impedance, and it behaves linearly when you do the operation. And these operational amplifier, they are basically like a black box building block of any analog electronic circuit or any electronic design, where what they do actually is they amplify the signal. So you can think of an op-amp as an electronic signal which goes into the input, and what the signal which comes out from the output is basically the bigger version of the input signal. So it's used in amplification, in analog filtering, it can be used in buffering, it can be used in any threshold detection, it can be used. Now let's see the next slide. Use of op-amps. So the op-amp, they can be configured in many different ways using resistors and other components. You can use and you can create different types of op-amps. So for example, with resistor and capacitor, you can make one type of op-amp. With resistor and inductor also, you can make another type of op-amp. So with different combination of these components, you can create the op-amp with its varied application. Most configuration, they use feedback. So in operational amplifier or op-amp, you use the negative feedback, and we will see how that negative feedback is basically put into the circuit. So let's see next. So now the different applications of an op-amp. Amplifier, it provides gain in voltage or current. Op-amp can convert the current to voltage. So op-amp can also convert the current source into the voltage source. Op-amp can provide a buffer between two circuits, where you will see this circuit where it basically acts as a buffer. And op-amp can be used to implement integrators or differentiators. So as I said in the previous slide, that you can use different combination of electronics component to create the op-amp. So integrator is one of that combination, in which you use like capacitor and resistors, and then you create an integrator. So we are going to study this integrator and differentiator in detail in next coming lectures. Now, other applications, the op-amp can be used in making the filters, low pass, band pass filters can be created using the operational amplifier. So here you see the symbol of op-amp. So these are the different, so let's first see the right picture. This is how it looks like. This is the symbol for operational amplifier, and you can see these are the different leads sticking out from the op-amp, and each of them has some purpose. So for example, this second lead, is your inverting input, and this your third lead is the non-inverting input. Now, if you compare this with this symbol, where this represents your IC, and in IC these are different pins, and these pins correspond to this. So, for example, at 2 point, at this point you have inverting input. So here you see the same thing, inverting input, and at 3 you have non-inverting input, and that's what you see here. And then similarly for the other points. So for example, at output point, you have output over here, and then you have a balance here, you have a no connection here at 8, and then you have at 7, you have V plus. So V plus has been shown over here, and then V negative is shown here at this pin, at pin 4. So at pin 4 is V negative, and then so we already saw this as the balance, and then 5 is also for use for balance. So balance is nothing, is just your offset null. So this offset null is basically used in an auxiliary circuit to compensate for a degradation in the performance of the op amp, and that can happen due to aging or any imperfection in the op amp. So this, however, this degradation which we sometimes see in the op amp in most cases are counted as negligible. So that's why these offset terminals or these pins which you see, these are usually not used. And then this was your no connection, or you can say NC. No connection means that that terminal is not connected to the amplifier circuit. So you will not be using this particular connection. Okay. So this is the symbol of operational amplifier, and let's move on to the next. So here you see is a schematic diagram of an operational amplifier. So what you saw in the last slide here, we just see all these pins sticking out from this operational amplifier, all these pins. But what is inside this integrated circuit is basically shown over here. So that's what it is there in this small chip which you'll be using in the lab. So this chip has internal circuit like this, and you will be implementing this circuit in your printed circuit board class, where you will be designing the circuit, and then you will be milling the board you created, and then you'll fabricate with all the components shown here. So this is the internal circuit, and you can see that how many transistors are used, resistors and capacitor combination makes this operational amplifier. And then if you notice the terminals which is coming out from this circuit are the same which you saw over here. So for example, here this positive, this negative is has been shown here, input, and so this inverting and non-inverting, and then you have offset, you have null here, you have VCC and VEE. So this is the supply which you are connecting here. So this positive V and this negative V basically goes to the supply, positive supply, and the negative supply. And the same thing is mentioned over here in this pin connection. So you connect 7 and 4 to the supply. This goes to the positive supply, and the other end goes to the ground. This goes to the negative terminal of the power supply. And so in this way, you basically construct, using these pin connection, you construct the op amp circuit. Now let's move on to next. So this was your internal circuit of an op amp. Now next we have the op amp model. So this is the simple op amp model, and we have two supplies here, V positive and V negative. These are the two supplies which are utilized in the operational amplifier. And then you see the input resistance by this capital RIN. This RIN is your input resistance, which is very high. And then you have output resistance, which is this R out, in series with the output voltage V0. So this is in series, and the value of this output resistance is very low. And then you have this again, coming back to here, this is a linear transfer function, where this is equals to output voltage. So like V naught is equals to A V plus minus V negative, where A is your open loop gain, and V naught is here, which is clamped at positive voltage here. So this is your simple op-amp model, and this terminal, which is the positive here, is called your non-inverting input, and the input which you send from here, the negative side, this is called your inverting input. Now, next we have is the typical op-amp, and then these are the same parameters which we saw here, and their typical range, their ideal values. So op-amp gain, so the gain is typically in the range of 10 raised to power 5 to 10 to power 8, and ideally for the ideal op-amp it will be infinite. So gain will be infinite in an ideal case, for an ideal op-amp. And the input resistance, which is Rn, is typically in the range of 10 to the power 6 to 10 to the power 13. And then ideally the input resistance is very, very high. So if the input resistance is very, very high, that means this point is going to be equal to this point. We will see this, there is a concept of a virtual ground because of this, and we are going to see in the next coming lectures. So till now you understood that the open loop gain of an amplifier, ideally it is infinite, and this is the range typically, and input resistance is also infinite ideally, and then this is the typical range. And output resistance is 0 ohm ideally, and practically it is from 10 to 100 ohms. Why do we need 0 ohm output resistance? Because if we have 0 output resistance, then we are going to have maximum output voltage, right? Because 0 ohm will basically allow all the voltage or the current, all the current to pass through the to the output, and you'll get the maximum voltage in that case. And that's the case of an ideal op-amp. Supply voltage VCC is from 5 to 24 volts. In the labs, you will be using around like 12 to 15 volts. So this was the typical range of an op-amp parameters, and these were the range for an ideal op-amp, its parameters range. Okay, so let's see an example. This is some op-amp, and in this op-amp we are giving some input supply to this negative terminal, and from positive terminal we have these resistances connected in this way. Okay, so 741 op-amp has an open loop gain of 2 into 10 raised to power 5. So here your A is the gain which is given. Input resistance of 2 mega ohm. Input resistance is usually high, so this value looks correct. And then output resistance of 50 ohm. The op-amp is used in the circuit shown below. Find the closed loop gain, which is A, and A is equals to V naught by Vs also. So that's your gain, and you have to find the output current when Vs is equals to 1 volts. So let's see, where is I naught? I naught is here, the current, output current, and Vs is this input voltage which has been given in the problem is 1 volts. So using these values and input resistance value and the gain value, we can find out, we can basically find out I naught and then closed loop gain. So what we will do, this is the same circuit from the last slide. we will first point out the nodes. So we have one node here which is Vs, and then you have V1 node here, and then you have V0 node over here. So if you see on the right, KCL has been applied to these nodes, and if you apply the KCL, that you will get these equation. First, let's apply the KCL, Kirchhoff current law, at V1 terminal. So we assume in the KCL that at a particular node, all the algebraic sum of all the currents will be equal to 0. Okay, in this so that's what we are going to use here, and this equation is based on that only. Algebraic sum of all the currents going out at this particular node will be equal to 0. So applying this KCL, you can apply in this way: V1 minus Vs upon this resistance. That's what is shown over here. V1 minus Vs upon 2 into 10 to the power 6 plus V1 V1 by this ground, which is at 0 potential. So you can either write V1 minus 0, or you can just simply write V1 upon 5 into 10 to the power 3, because it's 5 kilo ohm. And then the third branch will be your V1 and this V0. So V1 minus V0 upon 40 kilo ohm, and this will be made equal to 0. So once you have this equation, you can further simplify it, and you will get some equation in terms of V1 and Vs and V0. Vs, you already know it, which is 1 volts. You can put that value. And then at KCL at V0 we are going to find, which means at this node we are going to find. So if you find, then you're going to use first you're going to apply V0. So if we see this equation, so first term is R V0 minus this 0 ground upon 20 kilo ohm. So that's the same thing. And then second is V0 to this V1. So V0 minus V1 upon 40 kilo ohm. So that's your 40 kilo ohm plus V0 minus 2 into 10 to the power 5 multiplied by V1 minus Vs is what your input, this formula which you saw here. This is the same thing. And then so, and at this negative terminal, let's go back here. So yeah, so here you have this gain here, and then this is your V1 minus V minus minus Vs. You must be thinking, what is this V1, what is this Vs? So V1 is this, the positive basically positive supply which is going in here. That's why we have written V1. And then your Vs is this, so V1 minus Vs we have used here. And let's okay, so V1 minus Vs, it's because it's the same thing which is over here, plus and minus voltage. So you will use the same thing, V1 here, and then minus Vs upon 50 is equals to 0. So solving these two equations, you will get final equation, which will be V0 is equals to 9.0004 Vs. Vs is your 1 volts. So that means your voltage, output voltage for this particular case is going to be 9.004 volts. And then if you know the voltage, then you will just put the value of voltage into this particular branch, which is V0 upon 2 into 10 to the power 6 is equals to 0. You will just get the value of this current, because you know the value of output voltage. So that voltage divided by this 20 kilo ohm, that will basically give you the output current. Now let's see the ideal operational amplifier. So there are some assumptions which we take for an ideal operational amplifier. So first is the input resistance is infinite. So the input impedance of, or the resistance of the op-amp as viewed from the two input terminals is infinite. So you saw this input resistance over here. So this is your infinite. So that's one of the important property. And what does it implies? It implies that there will be no current which will flow either into or out of either input terminals of the op-amp. So you see that the two input terminals of the op-amp, so because of the high impedance or the resistance over here, there will be no current which will flow either into or out of this either input terminal of the op-amp. Thus, when several branches are connected to an input terminal of an op-amp, KCL can be applied to the node involved, as we saw previous example, that you can use the KCL to find out the current or voltage into the circuit of an op-amp. But the zero current in the op-amp, or the zero current which goes in here, that's the zero current. We assume that this is infinitely large impedance, and that's why there will be a zero current will go into this op-amp. And this zero current may be assumed for the op-amp input terminal current only in the ideal case. Now next is output. So this gain. So the gain is infinite, and gain A is equals to this is the sign of the infinity. So this is infinite. So open loop gain in case of an ideal op-amp approaches to infinity. So if gain is infinite, then what does it mean? So it means that your V plus will be equal to V negative. So think about this. Going back here, so if this is your infinite, then that means your V plus is equals to your V negative. So that's why in an op-amp you will see, which you will be seeing in the lab, you will see both the supplies are of same power. Okay. So zero output resistance R naught is equals to 0. So output impedance of the op-amp is viewed from the output terminal with respect to ground is basically 0 in an ideal case, and it implies that the output voltage at the output terminal does not change as the loading is varied. And the ideal op-amp will produce the same amount of output voltage irrespective of the current drawn into the load. So that's your that's the reason if you have if your output resistance is 0, and that's the case in the ideal op-amp. And then you have the op-amp is in a negative feedback configuration. So that's also very important, that op-amp which you'll be using will be typically used in negative feedback configuration, where some portion of the output is brought back to the negative input voltage V. Okay, so this was the basically important properties of an ideal op-amp. Now here next is the consequences of the ideal op-amp. So based on the first property, which says infinite input resistance, means the current into the inverting input is 0. So because of the infinite input resistance, what will happen? The current going into the op-amp. So let's go here. So imagine if this resistance is infinite, so the current going inside. So let's go here. So the current, if this is infinite, so there will be zero current going in, because this is infinite resistance, right? So resistance opposes the current. So you will have, if you have infinite resistance, then you will have zero current flowing in there. So that's what it says, that your I negative from one terminal and I positive from other terminal will be equals to 0. And the second important property of an ideal op-amp is the infinite gain. And because of that infinite gain, which is you will have a V positive minus V minus equals to 0. And infinite gain means the difference between the V plus and V minus, which is equals to 0. So if this 0, what does it mean? So V positive is equal to V negative. So these are the two important consequences of the ideal op-amp properties. And now let's see next. And so this is an example. Now in this example, so you saw this example previously which we did. This is the same example we did previously where we used KCL and applied into the whole equation, and we did not consider the ideal op-amp properties. You understand what I mean? So in the previous example, we did not assume the ideal op-amp, and so all the calculation is based on that, considering it is a non-ideal op-amp. But here, if you consider it is a ideal op-amp, and if you consider all the properties, then based on that, your equation will become super simple. So as you see here, we are so this this minus V naught is upon this is your 40 kilo ohm. So we are basically applying here KCL at this particular node. So Vs minus V naught is basically your 40 kilo ohm, and this Vs minus 0 volts upon 5 kilo ohm will be equals to 0, and then here this is going to be 0 because I plus current is 0, because we are assuming that input resistance is infinite. So this is going to be 0, so we don't have to include that. And if you just solve this, you will get 9 Vs is equals to V naught. So Vs is 1 volts, so you're going to get V naught is equals to 9 volts. And that's pretty much same you got in the previous example, where we did not consider it as an ideal op-amp. Now next node is this V naught node. So you see here this V naught node, applying the KCL at this particular node. So let's see, so we'll be including this branch, we'll be including this branch, and we'll be including this branch, right? Let's see. So this V naught minus Vs upon 40 kilo ohm, it's the same thing here. And then V naught minus 0 volts upon 20 kilo ohm, it's the same thing here. 0 I haven't used because it's obvious we will get the same thing. And then this is the current I naught is going into the V naught. So if any current is going into the node, then it will be taken as negative. So you can either assume as negative I naught is equals to 0. So that will be your algebraic sum of all the currents will be equal to 0. So that negative current has been taken here, and that's why you got this equation. So now you know the value of V naught already, which is 9 volts from this particular equation, and you know the value of Vs. So here you will get 9 volts divided by 20 kilo ohm plus V naught is your 9 minus 1 volts, so that means 8 volts upon 40 kilo ohm. So you simplify and you just do the math, and you will find out the output current, which is going to be 0.65 milliamps. So that's so you see that how the equations have become so simple, you considering the ideal op-amp properties, whereas if we go back and look at the equations, they were so big, and then for both the equation you had to solve, and then you finally get the equation in terms of V naught is equals to this voltage Vs, and then you can find the I naught. So it's a long process. Instead of doing that, we usually consider the ideal op-amp properties to make the calculation simpler. Now let's see. Next we have inverting amplifier. So you see here this is an op-amp, and why do we say it as inverting amplifier? Because the negative terminal is basically getting the supply. So this supply is connected to the negative terminal, and if it is connected to the negative terminal, then that is called your inverting amplifier. And there's other thing, the output which you're getting at the at here at V naught is inverted. So whatever the input you are giving, if you are giving something like this, then you will get the opposite output at the opposite waveform at the output. And that's why it's called inverting amplifier. That's the true reason. But to remember that which one is your inverting and which one is your non-inverting, simply just see that wherever is your negative terminal, that's your inverting. If your supply is connected to the negative, then that's your inverting op-amp. So here is your R1 resistance connected here, and this is your feedback RF. is your feedback, and then current I1 is going in here, some current is going in here, and then some part of current is going in this feedback loop, and then zero current is going inside this op-amp. Why? Because we are considering that the input resistance or input impedance, this is infinite. So if it is infinite, that means we have zero current going in here. And then these, and with the second property which we saw, the infinite output gain, we say that these input terminals, they are at the same potential. So if this is grounded, that means if this is at 0 volts, then this is also going to be at a 0 volts. Okay. So since our non-inverting terminal is grounded, so this is your plus, this is your non-inverting terminal which is grounded. So if it is grounded, that means we are going to get the same voltage at V1. So this is your V1, you will get the same voltage. So V1 is equals to V2 is equals to 0 by ideal property. Now, you know the potential at this particular point, you will just use KCL at this particular node V1, and then find out the value of I1 current and I2, and find the equation in terms of output voltage. So at V1, KCL at V1, so algebraic sum of all the currents will be equal to 0. So there are three currents which are there at this particular node. I1 is going in, and then I2 is going out, and then this zero current. So zero current which is going into this op-amp is ignored. So that means I1 is equals to I2. So that's what you see over here. And then, so I1 is equals to I2. I1 is what? I1 is basically V1 minus 0 volts, because V1 is 0 volts. So V1 minus 0 volts upon R1. And then this particular branch is equals to 0 minus V0. This is your V0 voltage minus V0 upon RF. So that's what you see here. Now you rearrange this equation and find out the value of V0. So V0, you will get negative RF by R1 into VI. So this negative sign which you see here is basically indicate your inverting output voltage. So if your V1 is, as I said, is whatever you get here is going to be inverted at the output. And this negative sign basically proves that. And this is very important equation. You have to remember it for an inverting amplifier op-amp. So where is the feedback? So feedback is here, and this feedback is your negative feedback. And you see that some portion of the output is brought back to the negative input here. So some portion of this output voltage is taken back as a feedback. So that's your inverting op-amp. So let's do quick review. To solve an op-amp circuit, we usually apply KCL. So always remember, we usually apply Kirchhoff current law. We find out the nodes where we want to apply the KCL and at one or both of the inputs. Okay. And then we invoke the consequences of the ideal op-amp. I negative is equals to I0 is equals to I plus. And V negative minus V negative, V positive minus V negative is equals to 0. So this is the extremely important property which you have to always remember when you solve the op-amp circuit. You will basically use this, and then the KCL you will apply at the node, and based on that you will find whatever you have to find in any particular problem. For example, output current or any current which is going into the feedback, etc. And then we solve for the op-amp output voltage. So if you want to calculate the output voltage, then you can calculate that if it's not given. Or so yeah, like there could be several cases of the problems for this op-amp amplifier, and we will see that in the next coming lectures. So this is all for today, and thank you so much for watching.